In this video, we're going to look at span. So we'd like to decide whether the vector w is in the span of vectors u and v. Well, let's start by remembering the definition of span. When we say the span of vectors u and v, that means the set of all possible linear combinations of u and v. So we could say it's a set of vectors that look like c1u plus c2v, where c1 and c2 are any real numbers. So if we now rephrase the question, we're wondering whether w is equal to c1u plus c2v. We could say let c1u plus c2v equal w. And then we're asking, does this system have a solution? So if this system has a solution, then yes, w is in the span of u and v. If the system does not have a solution, then no, w is not in the span. So let's set up this system as an augmented matrix. We'll take our vector u, and we're going to multiply that by c1, and we're going to add on c2 times vector v, and we're wondering whether that linear combination is equal to w. So there we go, there's our augmented matrix for the system, and we're going to try to put this in row echelon form. For this type of problem, it's not necessary to go all the way to RREF, so we'll simply go to the shorter REF. So let's do some Gaussian elimination. I usually like to get a 1 in the upper left-hand corner. Technically this is optional when you're doing Gaussian elimination, but I find it makes the calculations go a little bit smoother. In this case, it would be pretty easy to swap rows 1 and 2, so let's start by doing that. Second row will come up to the top, and our first row is going to go into the middle. Bottom row will stay the same. So we're going to use this one now as a pivot to eliminate the entries below it. We're going to get rid of the 4 and the 8. So let's do row 2 minus 4 times our pivot row, and we can also do row 3 minus 8 times our pivot row. So during row 2 minus 4 times row 1, we've got 0, minus 21, and positive 6. If we do row 3 minus 8 row 1, we've got 0, negative 39, and positive 11. So now we're going to move from our previous pivot, we're going to move down into the right over to this negative 21, and that's going to be the new pivot for our next step. So I find it a little bit easier here if we go through and divide row 2 by negative 21, so that we're creating a 1 in this position here. And if we watch our signs, this entry here over on the right is going to be negative 6 over 21, or you could call that negative 2 over 7 if you want. I'm just going to put an arrow here and show that just came from simplifying the fraction negative 6 over 21, just to keep the numbers a little bit smaller. So I just recopied the matrix from our previous step. Now that we've got a 1 here, last thing we want to do to get this into REF is just eliminate this minus 39 here. So let's take row 3 plus 39 times our pivot row, so that's row 3 plus 39 times row 2, and that will give us 0, 0. And for this entry on the right here, we'll need to do a little bit of a calculation. So we're going to take 11, and we're going to add on 39 times minus 2 over 7. Alright, so if we create a common denominator, we've got 77 over 7 plus, well this is really minus 78 over 7, so that's minus 1 over 7. Alright, so that entry is going to go in here. The important thing that we're realizing here is that this entry here is not 0, meaning as soon as we take a look at this bottom row here, we've got 0, 0 on the left-hand side, something non-zero on the right-hand side, we can conclude that the system has no solution. So just for completeness, I'm going to fill in the top 2 rows here, although technically at this point they don't matter to our solution. So the system that we originally set up has no solution. That tells us that no W is not in the span of U and V. We cannot find coefficients C1 and C2 so that W is a linear combination of U and V. Now, just as a follow-up here, I want to look at the geometric interpretation of this problem. Let's look at the geometry here. Vectors U and V represented 2 different directions in R3. We know that they represent 2 different directions because they're not multiples of one another. So when we start to look at the span of U and V, meaning we start with our vectors U and V, however they're positioned, we start to take all possible linear combinations of these vectors. We get all the multiples of U, we get all the different multiples of V, we get things that are combinations of the 2. What we'd be tracing out here is actually a plane in R3. So let's say that plane right there, that's our span. The question is whether W lies on that plane or not, and what we've concluded is that no, it doesn't. So in our picture here, maybe W might be coming up something like this.